Hello students, let us learn today the mechanism of sigmatropic rearrangement. So it is studied by the FMO method, frontier molecular orbital method. So let us take an example, 1,3-pentadiene. So 1,3-pentadiene thermally is going to give rise to 1,5 sigmatropic shift. And this is being the product. So here the change is that, so first we are going to number the substrate. So we have 1, 2, 3, 4, 5. And we can see that there is the allylic group also, which is the alkenyl chain, and we have D, which is numbered as 1, and this is the migrating group. So it migrates from 1, that is it is getting the number 1 to 5th position on the alkenyl group, alkenyl chain. That is why it is numbered as 1, 5 sigmatropic rearrangement. So according to the frontier molecular orbital theory, we should know that these substrates thermally will give rise to 1, 5 shift, whereas photochemically they give rise to 1, 3 shift. And the opposite is not possible. That is, thermally they do not give 1, 3 shift, and photochemically they do not give 1, 5 shift. So here we can see that 1, 5 shift is rather a very larger space. That is, like D has to travel to the 5th carbon and has to undergo the shift. Right? When you compare this with 1, 3 shift, it can easily undergo 1, 3 shift because the carbon number 3 is in the intermediate between the between 1 and 5 carbon atom. However, this shift is not possible. That is, thermally, these substrates do not give 1, 3 shift. They only give 1, 5 shift. Okay, so we will look at the mechanism now, how this is happening. So here we can see here how the D, that is a deuterium, is not getting bonded to the carbon 3. This is not observed. This kind of product is not observed. That is, thermally these shifts are only giving 1, 3, are giving only 1, 5, sorry, and not 1, 3 shift. Okay, so this can be studied by the frontier molecular orbital theory. So we have the substrate. Okay, so here this is a thermal reaction, and we will see how the substrates do not, they give only 1, 5 shift thermally. So now before that we have to understand that this reaction, or for the purpose of analyzing these orbitals, we are going to assume that this reactant is going to undergo a homolytic cleavage, which is going to give rise to the allylic groups. So let us see here how the reaction is happening. So this is the particular reactant, and here we can see it is again the hydrogen is the migrating group, and we have the allylic alkenyl chain, and it is again 1, 3 shift, because if you number it, it is 1, 2 and 3, and the migrating group which is bonded to the allyl carbon gets numbering 1. So hence from 1 it is shifting to the that is the alkaline chain, and hence it is the example for 1, 3 shift. So this is an example for 1, 3 shift sigmatropic reaction. So now we should assume, for our understanding or for analyzing the orbitals, we have to assume that this mechanism is happening by the homolytic bond cleavage. So homolytic bond cleavage, we know the homolysis is happening between the allyl carbon and the hydrogen. So it is going to give rise to a free radical, a hydrogen free radical, and an allyl free radical. So this is going to be the allyl free radical, which will, so we will see how these allyl free radical will bond, whether it will be symmetry allowed or whether it will be symmetry forbidden. So now we have to write down the molecular orbital structure for the allyl free radical. So this is going to be the molecular orbitals of allyl free radical. So we have, we should know that whenever we write down the molecular orbital for allyl free radical having carbon 3 carbon atom, so we are going to place a node in between. That is, here we are going to place a node, because according to the physical chemistry, we know that whenever you place a node, so it should have equal number of orbitals on both left and right side. So that is the reason why we place a node when it comes to odd number of carbon atoms, and we have to write down the orbital diagrams for odd number of carbon atoms. We usually place the node for, because here we can see that these are all same lobes or same size, same sign on the lobes, and hence it is referred as psi1. And for psi2, you cannot have, we cannot write down like plus plus minus. So if I write plus plus minus, then it will, I'm going to get a node here, and we cannot express the node in between, or we cannot have two orbitals and then a node and then again an orbital. It is against the rules of physical chemistry according to Schrodinger equation. So that's why we have to replace the orbitals with nodes. So that's why we write a node here. So now if you see the number of orbitals on left and right, they are 1 and 1 each, so it is equal. So that's why this is how we are going to write on the node. And whenever we, and an allylic free radical is having 3 carbon atoms, so it is in this form, right? And a carbon is having a node. So here you can see that there are 3 orbitals or 3 electrons. So here 2 electrons have been placed in the lowest energy level and 1 electron has been placed in the psi2. So psi2 is going to be the HOMO. So this will be our HOMO. Now there's going to be an interaction between HOMO and LUMO of another species. And we have the psi3, which is completely anti-bonding, and you can see there will be 2 nodes in the psi3. So now the HOMO of the allyl carbon, allyl free radical, is going to interact with the hydrogen. So we will see how it is, the interaction is going to happen. So first is we're going to see this is the HOMO. So HOMO is always having the opposite lobes. HOMO for the allyl free radical is having the opposite lobes, so plus and minus. And we have the hydrogen. Since hydrogen is electron deficient and it is a free radical, we are going to write as a plus. So hydrogen is being represented with a plus, and then we're writing it as hydrogen. So now the first kind of overlap. So here you can see that the hydrogen atom can overlap with the 2 orbitals of the allyl group. But if you observe carefully, we see that there is only a symmetry allowed on the left side. That is, the plus lobe of hydrogen can interact with the plus lobes of the p orbital, and then a bond can be formed. However, on the left side, that is when you look at the other lobe, it is having a negative sign. So the negative and positive cannot form any bond. So that is why, though it is geometrically possible, these become symmetrically forbidden. So hence we cannot see this kind of an interaction wherein the hydrogen is on the same side of the pi bond. So here the hydrogen is on the same side of pi bond, and this kind of interaction is not happening. So this kind of interaction wherein the 2 lobes are on the same side is what we call a suprafacial. So this kind of suprafacial interaction cannot happen because of these negative and positive lobes, which is totally not going to form any overlap, and this overlap is not going to be feasible, and hence this symmetry is forbidden. Now let us look at the second mode of migration. So the second mode of migration would be in such a way that the hydrogen is going to interact with the opposite ends of the lobes. That is, it is going to travel across the 2 lobes, and then it is going to form a bond. So that is how it has been represented in this way. Okay, so that is the hydrogen with a positive charge is going to interact or try to form a bond with the opposite signs of the, that is the lobes. Okay, because on the same side, it was not possible. On the same side, the hydrogen was not able to form a bond to give rise to the product. So hence, another way of how this approach or how the bond can be formed to give rise to the sigma-tropic shift would be in this way, in which the hydrogen with the lone pair, with the free radical on it, is going to bond or it is going to undergo an overlap in such a way that it is going to cross, or across the orbital, it is trying to go and form a bond. And here we can see that all the 3 phases or all the 3 signs on the lobes are plus, and hence this is symmetry allowed. But for the hydrogen atom to bond, because we can see here that the hydrogen is a very small atom, it is having the 1s orbital of hydrogen. So this cannot, and it is small, and it cannot, there is a distance between the 2 lobes of the interacting p orbital of the carbon is maximum. The distance between these is maximum. Hence, the orbital of this 1s, it cannot interact effectively with the p orbitals to form the product, or before that to form the transition state. So that is why, though this kind of an overlap is possible, though it is symmetry allowed, we can say that it is geometrically difficult because of the small size of the hydrogen, and it has to cross over for a very long distance between the two orbitals. So hence we can say that this kind of large distance which is being created between the two orbitals, and because of the small size of hydrogen, we can say that it would be geometrically difficult for this kind of an interaction to happen. So that is why these are the two main reasons why thermally this thermally it is not providing the 1,3 shift, though the carbon atom, though it is possible for the deuterium to attack at the carbon 3, to attach itself at carbon 3, it is not feasible because of these symmetry problems and the geometrical problems. So now let us see how this 1,3 shift is possible photochemically. Okay, so photochemically what is happening is through some radiations, and the electrons which are in the Psi2 get excited to the next higher energy level, that is going to be the Psi3 star. So now for photochemical reactions, the Psi3 star will be our new HOMO. Psi3 star will be the new HOMO, and the Psi3 star, since Psi3 star will be the new HOMO, and we can see this is going to be the orbital diagram for Psi3 star. And now this is going to interact with the hydrogen. So now here we can see very effectively how effectively the reaction is happening here. See, first is we are going to draw the orbitals. That is a HOMO. There is a new HOMO, or what we call that as a photochemical HOMO. And also we have the hydrogen here. So the hydrogen is here, and we have the new HOMO which is being made, that is a photochemically it has been obtained. So now you can see how there is an effective interaction of all the three lobes, and there is no, and it is geometrically also allowed and symmetrically also it is allowed. There is no hindrance in this kind of an interaction, and hence it is effectively, we can say that through FMO method, that the substrate can easily give rise to 1,3 shift photochemically, and it is not giving 1,5 shift photochemically. Okay, and thermally it is going to give rise to 1,5 shift. So let us see how this is happening. So for 1,5 shift, we have to consider the pentadienyl radical.